Okay, in this tutorial, we're going to focus on the cluster plot. What is it? How does it work? When can you use it? So here, let's just start by going right into it. You can see you start with it. It's a little spread out, which is kind of like a compromise thing here, but you can zoom out and then pan, and so you can see the whole thing here. Now, what's happening here is that you have a number of clusters, and those clusters are determined by the values for thickness, gloss, color, and texture. So all of those are taken into account when we cluster these items. So what you might say is that we have put every item in our collection in a four-dimensional space whose axes are thickness, color, gloss, and texture, and we have found like clumps in that space, right? And these clumps are the clusters. And then what we've done is, now the clumps are in 4 dimensions, so we can't, visualize that directly. But what we can do is we can take the centers of the clusters and then we can project them down into 2 dimensions. And then on that projection, we can rebuild the clusters in 2 dimensions as these little circles around each of the centers. And so you can see, like here, it's fairly obvious that there's an empty circle, there's an empty spot in the middle of this circle. And if we spread out a little bit, we can actually see this a little better. Every single one of these clusters has an empty square in the middle. And that is where the center is, right? And then sort of the cluster is built around that center. Now, you can't see this in the app, but the way that these clusters are built is kind of one step at a time. And what happens is that you have these 200 clusters, they have their centers, and as they populate this map here, they are allowed to add one member around the center of their cluster. And what you end up seeing sometimes is clusters colliding with each other, right? Because they have to take turns in adding their members, they sometimes want to use the same territory. They can't both use the same territory, and so that you end up having some of this like collision here, right? But the collision is actually interesting. And to get a better look at what that looks like, we're going to change the coloring of these points. So right now, all of the points are colored by their base color, right? So if you see more of a yellow looking point, that's a warm base color. If you see these bluer looking ones, that's a cool base color. And that's the coloring we have right now on the points. But we can actually change this to what's called radar group. And what a radar group is one of these clusters. The idea being that when you have a 4-dimensional representation of one of these papers, we can represent that on a radar chart that we call a glyph, right? Although glyph is a more general term than that. But that's why in this app we have tended to use the term radar because it's a radar chart. And that's a more specific term. And if 2 items have a very similar radar chart, and again, we're taking into account all 4 dimensions, thickness, color, gloss, and texture, then they will probably be in the same radar group. And so that's why we call these clusters radar groups. And we can see much better now, like, okay. So now we can see where groups are colliding into each other, like especially over here, where they're sort of on top of each other, but now we can distinguish, where the group lines are. You can also see that there's a bunch of these that have this purple color. These are, we sort of ran out of colors. The human eye can only distinguish so many colors visually at one time. And so once we get past a certain cluster number, we start with the biggest ones and kind of move down. Once we hit a certain point, they're all just the same color because I don't want to make these things confusing, right? So I want you to be able to, if you see a green colored item, know that it belongs to this cluster, and especially if we leave this view and we go to some other view like this histogram, I want you to be able to track these things, and I don't want you to get confused, like, oh, are these the green from the same cluster or not the same cluster, right? So like in this view, obviously they're much easier to distinguish, but in other views, like this, for example, you want to be sure that if you're seeing green, that it belongs to this particular cluster here. So that's why we only have a certain number of colors. Now you can change the colors by using this kind of color toggle. It's called the group color shuffle. And this just randomly assigns different color. I mean, there's a fixed list of colors that get used, but the specific mapping from that list to these cluster groups is just randomly assigned when you click this. And so when you land on something that you like, say maybe this, then these will be the colors. So one thing to see, so we do see there's kind of these interesting forms of collisions. We could see that these are four different clusters, but as we kind of bring them together, we see that they almost combine to make a mega cluster. And that's interesting, not just, I mean, it visually looks kind of cool, but it's also analytically interesting because it means that these different clusters are distinct, but they're probably fairly materially similar. So these are sort of like neighbor clusters. And you could view them as part of maybe a larger neighborhood, like a region of this map, and they live close together. That's kind of the idea. You know, if two things are near each other, they're similar. If they're very far, they're probably dissimilar, although I think that the local relationships are more accurate than the global ones. What's the relationship with other ways of visualizing this data? Well, one thing you can see is that, okay, we have these items colored by their radar group. Now let's look at them in three of the dimensions that get used in the radar group. So we already have color and thickness on the X and Y, and on the Z, let's put, say, gloss. Now this isn't going to change anything in the plot yet, right? Because the cluster plot has its own notion of an axis and everything. So these menus don't do anything when you're in the cluster plot layout. But if you switch from this layout to the 3D scatter plot, okay, so now we're looking at more sort of like the raw values, right, of these points. And then we have these kind of discrete groups as the colorings here. And we can see that these group boundaries are pretty well respected in this space. I mean, it also kind of shows you a little bit how arbitrary the grouping can be. You know, when you have a bunch of points in a continuous space like this, and the space is, you know, pretty evenly distributed, you know, these points are pretty evenly distributed throughout the space, it's hard to draw boundary lines, right? But you can see that generally speaking, those boundaries are pretty well respected here, which is what you would hope, right? So you have all of these, like, you know, purple items together and all these pinks here. And, you know, when you look at this kind of tangle of things here, you know, you got the blue and the orange and the yellow. When you go back to the cluster plot, you can see, oh yeah, that's right. There's the orange and the yellow, you know, they're still nearby. They're still near each other. And here's some of that blue, right? And so there's kind of like a sanity check on that you should expect these things to be near each other in both cases, because ultimately at bottom they're using the same information, but they're processing that information in slightly different ways. Okay, so once you're in this view, one thing you might be interested in doing is kind of looking at what are the characteristics of a particular cluster. And so let's say, and you might be particularly interested in, like, say, a smaller cluster. So like, here's a smaller cluster that like didn't make the cut for getting its own color. Okay. Now there's a couple things you can do here. Like one thing, so right now the sort of 3D representation of this thing is just a cube, and all the cubes are the same size, right? And so the only difference, you know, between the cubes on this page are that they have different colors. But you can actually change the representation from a plain cube to different things. And that can tell you a little bit about what's going on in these clusters. So one thing you can do is you can switch from a cube to a cube whose area is determined by the expressiveness of the paper. And expressiveness is just the sum of warmth, roughness, thickness, and mattness, you might say, lack of gloss, right? And so if the expressiveness glyph is bigger, that means it's a more expressive paper, and if it's smaller, it's a less expressive paper. And so here we see that generally speaking in these groups, we have fairly similar expressiveness glyphs. Occasionally, because of like binning artifacts and stuff, they won't be exactly the same, right? The way that we create these groups is like by binning some of these values, right? But generally speaking, you know, you have maybe slightly smaller cubes here, a few bigger cubes here. This is probably a slightly more expressive group. These are kind of like slightly bigger cubes. And you can see that's true. Now, some of these bigger clusters are a little bit more diverse. They have a little bit more diversity in these things. And again, you know, part of it is because there's like binning going on. So you have these kind of hard boundaries that are trying to partition a continuous space. And so you're going to get some kind of weirdness like that. another thing you can do is use what's called, right now it's called the isoglyph. And the reason it's called that is because the idea is that the thickness of the box, or maybe it's like the height of the box, is isomorphic to the thickness of the paper. So if you have a very tall box, like a cube shaped box, that's a thick paper. And if you have something closer to like a thin tile, then that is, here, let's try to find some of the thicker ones. Here we go. You can see some thin tiles and you can see some thicker things over here. And you can see some of that variation here, right? Yeah, you can see some of these things have kind of emerged as being a bit thicker right here. There's a bunch of thick ones over here, right? Those must be very thick papers. So those are probably fairly interesting papers. So then another thing we can do is if we want to kind of look at all dimensions of the radar chart at once, you can actually turn these little cubes into little radar charts. And this gives you a sense of what's going on in these clusters. And so let's zoom out a little and then let's like separate the clusters fully. Okay. And what you'll notice, so these glyphs are actually drawn to exactly match these radar groups. Because it turns out it's computationally expensive to draw the exact glyph for every item. So we have these like binned glyphs for each item, and they exactly follow the boundaries of these radar groups. And so in one of these groups, you'll be able to see they all have, exactly the same glyph. But that's neat then, because if you want to get the sense of what's going on in an individual group without having to look in the panel or whatever, you could say, okay, these are pretty high color, because that's the top axis, the bottom axis is roughness. So these are kind of smooth despite having some high color, and then they're fairly matte and fairly thick. So these are pretty expressive glyphs. And so if we were really interested in them, then we could select all of these with a box select. They go into the panel, and now we can take a closer look at these. We can, for example, look at their textures. There's kind of a lot of different textures going on, but mostly on the rough side, right? If we look at their colors, we're seeing colors kind of on the, on the warm side, which is what we should expect given the glyph. And by the way, if we want to look directly at their glyphs here, and we can kind of like remove some of the text here, we can see that yes, these are fairly big glyphs. And we can also then see the difference between this binned form of the glyph, this kind of discretized form of the glyph, where these are all the same. These are not all the same over here. And there's some variation here, but again, it shows you that when you create these very kind of like sharp breakpoints, and then you treat those as being as items within the same bins that are defined by these breakpoints as being the same, you can you're glossing over some variation. So this is sort of like the raw data, and then this is kind of like the binned data. Mm-hmm. So anyway, this gives you a sense of what the cluster plot is telling you. Let's go back to the normal glyph. And you can use it primarily if you're trying to find items that are very similar overall, or for example, like we'll talk about one kind of use case here. So let's go back, okay, and just make it a grid. Let's say, for example, that you are interested in, well, I guess we can leave it like that. Let's say you're interested in a particular like brand. Okay, you're very interested in like Azo. Okay, great. And then you are interested in maybe something else. Maybe you want to also look at rough Azo. Okay, so like that's not like a whole ton, right? So let's add those to the panel, and okay, we can see that there. Maybe let's just go back to this, and we'll add some text in there. Okay, so now we have these items highlighted, and now we can go into the cluster plot, and we can, let's go back to maybe like base color or something like that, right? And now we can see where they sit. So we were just interested in Azo, and we were interested in a particular texture of Azo, like a rough texture of Azo. And we can see that they're actually like spread out a little bit, right? If you view the cluster plot as sort of like a similarity space for these papers, Yeah, they're not all exactly the same. There's some differences there, and we could look at maybe why that is. Well, yeah. So I mean, the roughnesses probably should be pretty similar because these are all called rough papers. The colors differ quite a bit. This one's quite warm, and this one is not. Right. This actually looks pretty cool. We might, for example, be interested in their thicknesses, and so we could look more specifically at that. Like if we wanted to do that, maybe we would do like a thickness histogram here, and we could see where they sit with respect to thickness. So like we have a really thin one over here at 0.15, probably like a single weight, but then we have a bunch that are quite thick. And in fact, this is extremely thick, almost 0.5. That's a very thick paper. So that's one way in which they differ, despite being similar in other ways. They're all azo, they're all rough or whatever. So this is how you can use the cluster plot as just like a proxy for overall material similarity. And then if there are other things you're interested in and you want to see sort of like how similar these items are, the cluster plot feature can help you do that.